Okay, so last scenario, we'll look at k equaling 10 and solving this differential equation. So the auxiliary equation, m squared plus 10m plus 25. I've missed out an x, haven't I? I'm sorry. Equals 0. And that gives you that m is equal to minus 5. So you've got a repeated root and the discriminant is equal to 0. And so the general form of that is a plus b t e to the minus 5t. And again, initial boundary conditions give you a and b. So when a equals 0, t equals 0. And if you substitute that in, that gives you a equaling 0. And so x is equal to b t e to the minus 5t. And then differentiating to get the velocity. So if I differentiate the t, I get 1. And then if I differentiate e to the minus 5t, I get minus 5 e to the minus 5t. And when t is 0, v is equal to 1. That's right, isn't it? Yeah. And so from there, 1 is equal to b, because that's going to 1, that's going to 0. And so this equation here, x is equal to t e to the minus 5t. Sketching this one, the sketches of these will all come out a little bit differently. A bit like with the heavy damping, we'll call it over damping. If you were to differentiate this, which we've done up here, then you can find stationary points. So just substituting into here, b is equal to 1. So I've got e to the minus 5t minus 5t e to the minus 5t. Then you can pull out e to the minus 5t as a factor. And then if you want to find where the gradient is equal to 0, e to the minus 5t can't equal 0, and so 1 minus 5t equals 0, and so t is equal to a fifth. So there's a stationary point at t equals a fifth. It will be a maximum. You don't need to sketch these, so you're not going to be given a question to do in a sort of test condition where you need to sketch these. But when t is a fifth, I've got this maximum point, and I know when x is 0, t is 0, and there won't be any oscillations for these. So this is coming up like so to here, and then this term is basically going to take over, and as t approaches infinity, 1 over e to the 5t is going to approach 0 much quicker than t. I know t is going to infinity anyway, isn't it? So, but it's going to get bigger a lot quicker than t, so the whole thing will approach 0, like so. So the graphs for where the discriminant equals 0 are very similar to the heavy damping graphs. It's quite difficult to sort of tell them apart. So a few things to note. The discriminant of the auxiliary equation is equal to 0. And this is known as critical damping. So it's where you go from light damping to heavy damping. And the oscillations stop, basically. The pattern of motion can be similar to overdamping. It may not actually be as similar as this one, but it often is. So, pattern of motion, often similar to heavy damping. But you don't need to really worry about these graphs, but critical damping is where the discriminant is equal to 0, and it goes from light damping to heavy damping.